In this video series, we will discuss how to solve Newton's second law problems. If you find that these video explanations move too slowly, you can use the solutions documents to supplement or replace the video explanations. And you can use the table of contents in the progress bar to skip to particular topics in the video. Now let's try our first Newton's second law problem. Please pause the video and try this problem. Now let's discuss the problem together. Here's a summary of the solution to the problem. Now let's discuss the solution, step by step. Here are some YouTube controls which you may find useful while you're watching the videos. The problem mentions the concepts of mass, tension, which is a force, friction, which is a force, and acceleration. All of those concepts can be substituted into the Newton's second law equations. So we plan to use the Newton's second law problem-solving framework to solve this problem. Here's a handout which summarizes the step-by-step process for solving Newton's second law problems. You can find a link to this handout in the video description box. You should print out this handout so that you can follow along with the steps as we proceed through the solution. Now, the problem has already provided us with a sketch, so let's begin by making a note of what the question is asking us for. The question asks for the magnitude and direction of the acceleration. When possible, you should try to represent what the question is asking you for with a symbol. Notice that the symbol A, written without an arrow on top, stands specifically for the magnitude of the acceleration vector. Draw the block's velocity vector. The direction of the velocity vector indicates the object's direction of motion. The orientation of the rope in this sketch implies that Jessica is dragging the block to the right. So we draw the velocity vector pointing to the right. Here's a summary of the steps that we've completed so far. This step isn't relevant for this problem because this problem is numeric, not symbolic. Now, we're ready to work on the free body diagram. We usually need to draw a free body diagram for the object whose mass is mentioned in the problem. This problem mentions the mass of the block. So, we will draw a free body diagram showing all the forces being exerted on the block. Later, we will apply our Newton's second law equations to the block. Here's a general two-step process for identifying all the forces for your free body diagram. First, draw a vector to represent the weight force. We will represent the weight force with the symbol lowercase w. The weight force can also be referred to as the gravitational force. Next, we systematically ask what is touching the object. For this problem, we ask what is touching the block. The block is being touched by the table. The table is treated as a surface. A surface can exert both a normal force and a frictional force. The problem confirms that there is friction between the table and the block. We will represent the normal force with the symbol lowercase n, and we will represent the frictional force with the symbol lowercase f. The block is sliding along the table, so the table will exert a kinetic friction force rather than a static friction force on the block. We will represent the kinetic friction force with the symbol F sub k. Are there any other forces on the block? Well, ask yourself, is there anything else that is touching the block besides the table? Yes. The block is also being touched by the rope. We will use the term tension force for the force exerted by a rope. We can represent the tension force with the symbol uppercase T. Are there any other forces on the block? Well, ask yourself, is there anything else that is touching the block besides the table and the rope? No. There is nothing else that is touching the block. So, there are no other forces being exerted on the block. Always label every vector arrow that you draw. Drawing vector arrows without labels leads to confusion and mistakes. You should now pause the video and memorize this two-step method for identifying all the forces for your free body diagram. The key to this method is to systematically ask yourself what is touching the object. The purpose of the free body diagram is to indicate the directions of each of the forces on the object. Here's the rule for determining the direction of the weight force. The weight force always points straight down. Here's the rule for determining the direction of the normal force. The normal force points perpendicular to and away from the surface that is touching the object. In this problem, the surface that is touching the block is the table. So, the normal force points perpendicular to and away from the surface of the table. So for this problem, the normal force points up. Here's the rule for determining the direction of the kinetic friction force. The kinetic friction force exerted by a surface on an object points parallel to the surface and opposite to the direction that the object is sliding. The kinetic friction force exerted by the table will be parallel to the table. The block is sliding to the right, so the kinetic friction force points to the left. Friction opposes sliding. Here's the rule for determining the direction of the tension force. The tension force exerted by a rope on an object points parallel to the rope and away from the object. So, the tension force exerted by the rope on the block points parallel to the rope and away from the block, like so. You should pause the video and memorize these 4 rules for determining the directions of the weight force, normal force, kinetic friction force, and tension force. Here's a summary of the steps which we completed for drawing the free body diagram. Next, we work on the force table. The purpose of the force table is to organize the data, which we will be substituting into the Newton's second law equations. In the first row of the force table, we represent the magnitudes of each of the overall force vectors. A magnitude is a number that can be positive or 0, but that can never be negative. Remember that a vector symbol written with an arrow on top stands for the complete vector, including both direction and magnitude. But a vector symbol written without an arrow on top stands just for the magnitude of the vector. The purpose of the first row of the force table is to represent the magnitudes of the forces. So we write the symbols in the first row of the force table without arrows on top. In contrast, the purpose of the free body diagram is to represent the directions of the forces. So we write the symbols in the free body diagram with arrows on top. Here is a 3-step method for how to represent the magnitude of each of the overall force vectors in the first row of your force table. The magnitude of the tension force is given in the problem, 20 newtons. So we use that value to represent the magnitude of the tension force in the first row of our force table. There is a special formula for the magnitude of the weight force, W equals mg. Can you say exactly what each of the symbols in this formula stands for? Well, here's the answer to that question. The symbol W, written without an arrow on top, stands for the magnitude of the weight force. The symbol m stands for the object's mass. Don't confuse the mass with the weight. The symbol little g, written without an arrow on top, stands for the magnitude of the acceleration due to the Earth's gravity. Little g is a physical constant equal to 9.8 meters per second squared. The problem tells us that the block's mass is 3 kilograms. For little g, we substitute 9.8 meters per second squared. Then we can calculate that the magnitude of the weight force is 29.4 newtons. We write that result here in the first row of our force table. There is also a special formula for the magnitude of the kinetic friction force. F sub k equals mu sub k times little n. Can you say exactly what each of the symbols in this formula stands for? Well, here's the answer. The symbol F sub k, written without an arrow on top, stands for the magnitude of the kinetic friction force. This symbol is the Greek letter mu, so this symbol is pronounced mu sub k. Mu sub k stands for the coefficient of kinetic friction. Don't confuse the force of friction with the coefficient of friction. The symbol n, written without an arrow on top, stands for the magnitude of the normal force. The problem tells us that the coefficient of kinetic friction is 0.2, so we substitute 0.2 for mu sub k. We don't know the magnitude of the normal force yet, so we will continue to use the symbol n, written without an arrow on top, to stand for the magnitude of the normal force. So we can represent the magnitude of the kinetic friction force with the mathematical expression 0.2n. We write that mathematical expression here in the first row of our force table. There is no special formula for the magnitude of the normal force, and we were not given a value for the magnitude of the normal force, so we simply represent the unknown magnitude of the normal force with the symbol little n, written without an arrow on top. We already used the symbol n in our expression for the magnitude of the kinetic friction force. If there's no special formula for the magnitude of a force, and we're not given a value for the magnitude, then we simply represent the unknown magnitude of the force with a symbol in the first row of our force table. For purposes of filling out your force table, don't try to figure out how all these forces will interact with each other. You can let the Newton's second law equations figure out those interactions for you later in your solution. Before you break the forces into components, you must choose your axes. It's usually best to choose an axis that points in the object's direction of motion. The block is moving to the right, so let's choose a positive x-axis that points to the right, and let's choose a y-axis that points up. Always write down your axes. Now we're ready to break the forces into components. The normal force is parallel to the y-axis, the kinetic friction force is anti-parallel to the x-axis, and the weight force is anti-parallel to the y-axis. So we can use this rule to break all three of these forces into components. The weight force points down, which is our negative y direction. So W sub y is negative. W sub y has the same magnitude as the overall weight force, 29.4 newtons, and the other component, the x component, is 0. It's crucial to include this negative sign on W sub y. The normal force points up, which is our positive y direction. So n sub y is positive. N sub y has the same magnitude as the overall normal force, which we are representing with the symbol n. And the other component, the x component, is 0. The kinetic friction force points left, which is our negative x direction. So the x component of the kinetic friction force is negative. The x component has the same magnitude as the overall kinetic friction, which we are representing with the mathematical expression 0.2n. And the other component, the y component, is 0. It's crucial to include this negative sign on the x component. Again, it is crucial to include the negative signs in front of W sub y and F sub kx. If you leave out those negative signs, you will get the problem wrong. So, I recommend that you should include a plus sign in front of positive components, like n sub y, because that will help you to notice when you need a negative sign in front of negative components. The tension force is neither parallel nor anti-parallel to either axis, so we can't use this rule to break the tension force into components. Instead, to break the tension force into components, we will have to draw a right triangle and use the SOHCAHTOA equations. Here's the process for breaking the tension force into components. Remember that if you feel that you've already mastered the skill of breaking a vector into components, You can use the table of contents in the progress bar at the bottom of the video to skip ahead to the next topic. Draw the legs of your right triangle parallel to your axes. For this problem, we chose horizontal and vertical axes. So for this problem, we draw a right triangle with horizontal and vertical legs. Label the three sides of the right triangle. The hypotenuse of the right triangle represents the overall tension force. This leg represents T sub x because it's parallel to the x-axis. This leg represents T sub y because it's parallel to the y-axis. Draw the directions of the components. In this case, the overall vector points up and right. So the y component points up and the x component points right. Before we determine the magnitudes of the components, let's determine the signs of the components. T sub x points right, which is our positive x direction, so T sub x is positive. T sub y points up, which is our positive y direction, so T sub y is also positive. Label this 60-degree angle at the bottom of the triangle with an asterisk to indicate that our SOHCAHTOA equations will focus on that 60-degree angle, rather than on the 30-degree angle at the top of the triangle. Label the sides. This leg is labeled as adjacent because it is adjacent to the 60-degree angle that we're focusing on. This leg is labeled as opposite because it is opposite to the 60-degree angle that we're focusing on. And this side is the hypotenuse because it's across from the 90-degree angle. Our memory aid, SOHCAHTOA, reminds us that sine equals opposite over hypotenuse, so, and cosine equals adjacent over hypotenuse, ca. In this case, our labels on the triangle show us that the length of the opposite side represents the magnitude of T sub y, and the length of the adjacent side represents the magnitude of T sub x, and the length of the hypotenuse represents the magnitude of the overall tension force, which the problem told us is 20 newtons. We use absolute value symbols in the SOHCAHTOA equations to indicate that the SOHCAHTOA equations can only tell us the magnitudes of the components. It is our job to determine the signs of the components in a separate step. We already decided that each component is pointing in the positive direction, so both components are positive. For this problem, we used sine for the y component and cosine for the x component, but you will see other problems in which you need to use sine for the x component and cosine for the y component. So don't assume that you will use sine for y and cosine for x on other problems. Use the SOHCAHTOA process that we've illustrated here to determine the correct approach for each individual problem. It is important to master the skill of breaking vectors into components. You can find more help with that skill in my previous video series on vector components. You can find a link to that series in the video description box. Now we can add our results for T sub y and T sub x to our force table, like this. Remember, you should include a plus sign in front of positive components, like T sub x, T sub y, and N sub y, because that will help you to remember to include the crucial negative signs in front of negative components, like W sub y and the x component of the kinetic friction. Here's a summary of the steps which we completed for filling out the force table. Here's another handout which summarizes some of the key information you should be familiar with about the weight force, the normal force, the tension force, and friction force. You can find a link to this handout in the video description box. Now we're ready to work with the Newton's second law equations. We write two Newton's second law equations, one for the x component and one for the y component. I recommend that you write those two equations at the top of two adjacent columns. Now, can you say exactly what each of the symbols stands for in these equations? Here's the answer. M stands for the object's mass. A sub x stands for the x component of the object's acceleration. A sub y stands for the y component of the acceleration. This symbol is the Greek letter sigma. Sigma means add. So this expression tells us that on the left side of this equation, we should add all the x components of the forces on the object. And this expression tells us that on the left side of this equation, we should add all the y components of the forces on the object. Remember, these two equations are referred to as the Newton's second law equations. We take the components for our Newton's second law equations from our force table. On the left side of the Newton's second law x equation, we add the x components of the forces. 0 plus 0 plus negative 0.2n plus 10 newtons. And on the left side of the Newton's second law y equation, we add the y components of the forces. Negative 29.4 newtons plus n plus 0 plus 17.3 newtons. Be sure to include the negative signs when you add negative components. For the mass, we substitute 3 kilograms. If an object is motionless in a component, then that component of its acceleration is 0. In this problem, the block is moving horizontally in the x component. The block is motionless vertically. The block has no motion in the y component. Because the block is motionless in the y component, a sub y equals 0. So, we can substitute 0 for a sub y in the Newton's second law y equation. In an introductory physics course, most Newton's second law problems will have an object that's motionless in at least one of the components. So you will need to substitute 0 for at least one acceleration component for most Newton's second law problems. There's no reason to substitute 0 for a sub x. In fact, a sub x is what we need to figure out in order to answer the question. So we continue to use the symbol a sub x in our Newton's second law x equation. We've organized our math into 2 adjacent columns. Newton's second law x equation in the left column, and Newton's second law y equation in the right column. At this point, the Newton's second law x equation has 2 unknowns, n and a sub x, so we postpone working with this equation. The Newton's second law y equation has only 1 unknown, n, so we're ready now to solve this equation for n. We obtain the result that n equals 12.1 newtons. Next, we substitute our result for n into the Newton's second law x equation. After we do that, the Newton's second law x equation now has only 1 unknown, a sub x. So now we're ready to solve the Newton's second law x equation for a sub x. Our result is that a sub x equals positive 2.53 meters per second squared. Remember that it's a good idea to include a plus sign in front of a positive component. We've arranged our math in 2 adjacent columns. All the versions of the Newton's second law x equation in the left column, and all the versions of the Newton's second law y equation in the right column. This helps us to keep our math organized, so you should imitate this 2-column approach in your own work on Newton's second law problems. Now we're ready to answer the question. We've determined a sub x and a sub y, the components of the acceleration. The question is asking for the magnitude and direction of the overall acceleration vector. But since a sub y is 0, we know that the magnitude and direction of the overall acceleration vector will be the same as the magnitude and direction of a sub x. A sub x is positive. Our positive x direction is right. So the overall acceleration vector points to the right, as I've drawn here. The magnitude of a sub x is 2.53 meters per second squared. So the magnitude of the overall acceleration vector is also 2.53 meters per second squared. In my final answer, I've rounded that result to 2 digits. Here's a summary of the steps which we completed for using the Newton's second law equations. Actually, we have one more check left to make. We still need to check whether our results make sense. Let's begin by checking whether our results for the y component make sense. Our result for n is positive. Does that make sense? Well, the symbol n, written without an arrow on top, stands for the magnitude of the normal force. A magnitude can never be negative, so yes, it does make sense that our result for n is positive. If our result for n were negative, we would know that we'd made a mistake. Now, we found that the magnitude of the normal force is 12.1 newtons, the magnitude of the weight force is 29.4 newtons, and when we broke the tension force into components, we found that the magnitude of T sub y is 17.3 newtons. Do those results make sense? In this version of the free body diagram, I've broken the tension force into components. We found earlier that the components of the tension force point up and right. So in this version of the free body diagram, I've drawn the components of the tension force pointing up and right. The downward weight force is trying to make the block begin moving downward. To prevent the block from beginning to move downward, the weight force must be canceled by the cooperation between the upward normal force and the upward T sub y. So we expect that the magnitude of the normal force plus the magnitude of T sub y must equal the magnitude of the weight force. Well, 12.1 newtons plus 17.3 newtons does indeed equal 29.4 newtons. So yes, our results for the y component do make sense. In this version of the free body diagram, I've drawn the length of the weight force arrow equal to the sum of the lengths of the normal force arrow and the T sub y arrow to reflect the relationship between those three forces. Now let's ask, do our results for the x component make sense? Our result for a sub x is positive. Does that make sense? The friction force is pulling to the left, while T sub x is pulling to the right. When we broke the tension force into components, we found that the magnitude of T sub x is 10 newtons. And during the course of our work on the Newton's second law x equation, we found that the magnitude of the kinetic friction force is 2.42 newtons. So, the magnitude of T sub x will exceed the magnitude of the friction force. This means that the net force on the block will point to the right. In this version of the free body diagram, I've drawn the arrow for T sub x longer than the arrow for the friction force to reflect that relationship. The net force is the sum of all the individual forces. This symbol stands for the x component of the net force, and this symbol stands for the y component of the net force. According to Newton's second law, the net force at a particular point in time determines the acceleration at that point in time. Since the net force on the block is to the right, the acceleration will be to the right, as I've drawn here. And right is our positive x direction. So yes, it does make sense that our result for a sub x is positive. Don't confuse velocity with acceleration. The direction of the velocity vector indicates the object's direction of motion. In this problem, the block's velocity points to the right because the block is moving to the right. The direction of the acceleration vector does not indicate the object's direction of motion. So, what does the acceleration indicate? In physics, acceleration refers to increasing speed or decreasing speed or changing the direction of motion. Here are some rules that we can use to help us interpret the acceleration vector. In this problem, the block's acceleration vector is parallel to the velocity vector. Vectors are parallel when they point in the same direction. So, based on this rule, the block's rightward acceleration tells us that the block's speed is increasing. In this problem, T sub x is trying to speed up the block. The kinetic friction force is trying to slow down the block. The magnitude of T sub x exceeds the magnitude of the kinetic friction force, so the block will speed up. Now, let's do a recap of our work on this problem. The purpose of this problem was to introduce the step-by-step method for solving Newton's second law problems. The basic process is first, free body diagram, then force table, then Newton's second law equations. The purpose of the free body diagram is to represent the directions of the forces. The purpose of the first row of the force table is to represent the magnitudes of the forces. And the purpose of the second and third rows of the force table is to represent the components of the force vectors. We use the directions of the forces from the free body diagram together with the magnitudes of the forces from the first row of the force table, together with the axes that we have chosen to determine the components of the forces for the second and third rows of our force table. Then we add the components from the second and third rows of our force table on the left-hand sides of our Newton's second law equations. Let's look again at some of the details of that overall process. Use this general two-step process to identify all the forces for your free body diagram. The key to this process is to systematically ask yourself what is touching the object. Use this three-step process to represent the magnitudes of the forces in the first row of your force table. Include plus signs in front of positive components because that will help you to remember to include the crucial negative signs in front of negative components. In this problem, the block was motionless in the vertical y component, so we were able to substitute 0 for a sub y in our Newton's second law y equation. How do we know what order to work with the Newton's second law equations? By counting the unknowns. We began with 2 unknowns in the Newton's second law x equation, so we postponed working with that equation. We had only 1 unknown, n, in the y equation, so we began by solving the y equation for n. Then we substituted our result for n into the x equation. At that point, the x equation had only 1 unknown, a sub x, so we were then ready to solve the x equation for a sub x. Arrange your math for the Newton's second law equations in 2 adjacent columns, like this, since that will help you to keep the math organized. To succeed with Newton's second law problems, think in terms of components. Let me ask you a question. The problem gave us this number of 20 newtons. The question is, where did we substitute that 20 newtons number into our Newton's second law equations? Well, here's the answer. We did not substitute the 20 newtons into the Newton's second law equations. Instead, we broke the 20 newtons into components. Then we substituted those components into the Newton's second law equations. That's a great example of the importance of thinking in terms of components. Here's a few other examples of the importance of thinking in terms of components for this problem. We write down 2 versions of the Newton's second law equations. 1 equation for the x component and 1 equation for the y component. In our equations, notice how differently we treated a sub x, which we left as a variable, and a sub y, for which we substituted 0. And remember that thinking separately about t sub x and t sub y was crucial for helping us to understand why our results made sense. Try to use the exact right symbols, including the exact right subscripts. Use x and y subscripts to distinguish the components from each other. Use careful symbols to distinguish each of the forces from each other. A vector symbol written with an arrow on top stands for the complete vector, including both direction and magnitude. A vector symbol written without an arrow on top stands just for the magnitude of the vector. And remember that a magnitude is a number that can be positive or 0, but that can never be negative. Why should you make an effort to use the exact right symbols? Well, if you use the wrong symbols, you're likely to mix up the concepts, and then you're likely to use the wrong concepts at the wrong points in your solution. Using the exact right symbols is a tool to help you avoid mixing up the concepts. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge at my Patreon page. You can visit my Patreon page by clicking the link on the screen, or by using the link in the video description box. Thank you.